Welcome to Organic Chemistry. Have you ever wondered why two molecules made of the exact same atoms can behave in completely different ways? Today, we are going to explore the fascinating three-dimensional world of diastereomers. We will also learn how chemists use light to measure and identify these unique molecules through a property called specific rotation. Let us dive in. To start, let us imagine a pair of shoes. A left shoe and a right shoe are perfect mirror images, which in chemistry we call enantiomers. But what if you mix them up? A left sneaker and a right boot are both shoes, but they are not mirror images. In the molecular world, we call these diastereomers. They are stereoisomers that share the same atoms and connections, but their three-dimensional arrangement makes them non-mirror images. Think of them like siblings. They share parents and features, but they are not identical twins. Because their shapes are fundamentally different, diastereomers have completely different physical properties, such as different boiling points and densities. Now that we understand what diastereomers are conceptually, let us look at how they form. The key lies in chiral centers. A chiral center is simply a carbon atom bonded to four completely different groups, giving it a specific three-dimensional handedness. To have diastereomers, a molecule usually needs at least two of these chiral centers. If you take a molecule and flip the 3D arrangement at every single chiral center, you get its mirror image, an enantiomer. But if you flip the arrangement at only some of the chiral centers while keeping the others exactly the same, you create a diastereomer. You are changing part of the molecule's shape, but not the whole thing. This brings us to an important question. How many possible three-dimensional variations can a molecule have? We can calculate the maximum number of stereoisomers using a simple formula, 2 raised to the power of n. Conceptually, every time you add a new chiral center, the number of possible 3D shapes generally doubles. In this formula, n represents the total number of chiral centers in the molecule. However, there is a catch. If the molecule has an internal plane of symmetry, making it overall symmetric, it is called a mesocompound. Mesocompounds are identical to their mirror images, which means the actual number of unique stereoisomers will be less than 2 to the power of n. Now that we know how to count these 3D molecules, let us look at how we measure them in the lab. Chiral molecules have a special superpower. They can physically twist light. If you shine plain polarized light, where all waves move in the exact same direction, through a sample, the molecules will twist the light to the left or right. But the amount of twist depends on how many molecules the light bumps into. A longer tube or a more concentrated liquid means more twisting. To compare different molecules fairly, scientists created a standardized measurement called specific rotation. Just like calculating miles per gallon for a car, specific rotation measures a molecule's built-in ability to twist light under strict standard conditions. Let us look at the mathematical formula used to calculate this standardized value. The specific rotation, denoted by the symbol alpha in brackets, equals the observed rotation divided by the product of concentration and path length. The observed rotation, just alpha, is the actual angle the light twisted during your specific experiment, measured in degrees. The variable C is the concentration of your solution in grams per milliliter. Finally, L is the path length of the tube holding the sample, measured in decimeters. Remember, 1 decimeter is 10 centimeters. If you increase the concentration or the tube length, the observed rotation will increase. But the specific rotation remains exactly the same because it is a fundamental constant of that molecule. Before we calculate anything, let us visualize this process with a diagram of a polarimeter. On the far left, we have a standard light source, emitting unpolarized light, waving in all directions. This light passes through a polarizing filter, which blocks everything except waves moving in one single vertical plane. This plane polarized light then enters the sample tube containing a chiral solution. As the light travels through the tube of length L and concentration C, you can see the chiral molecules physically twisting the light wave. Finally, the light exits and hits a detector dial on the right. The angle it has twisted from the vertical is our observed rotation, alpha. This is the exact setup that gives us the numbers for our formula. Now that we have seen the instrument, let us solve a concrete example. A student dissolves 2.0 grams of a chiral compound in enough water to make 10.0 milliliters of solution. The sample tube is 5.0 centimeters long and the observed rotation is positive 1.5 degrees. We need to find the specific rotation. First, we must ensure our units match the standard formula. We calculate the concentration, C, by dividing the mass by the volume, giving us 0.2 grams per milliliter. Next, the path length must be in decimeters. Since there are 10 centimeters in a decimeter, we divide 5.0 by 10 to get a path length of 0.5 decimeters. We now have all our standardized units ready. Continuing with our calculation, we bring in the standard specific rotation formula. We plug in our observed rotation of positive 1.5 degrees in the numerator. In the denominator, we multiply our concentration of 0.2 by our path length of 0.5. Multiplying the denominator gives us 0.1. Finally, dividing 1.5 by 0.1 gives us a specific rotation of positive 15 degrees. Physically, this means that if you had a perfectly standard solution of 1 gram per milliliter in a 1 decimeter tube, this specific molecule would always rotate the light by exactly 15 degrees to the right. Let us look at a different scenario. What if we already know the specific rotation and want to predict what the machine will read? The specific rotation of pure cholesterol is negative 31.5 degrees. A scientist prepares a solution with a concentration of 0.05 grams per milliliter in a tube that is 2.0 decimeters long. What is the observed rotation? Here, we start with our standard formula, but we need to rearrange it. By multiplying both sides by the concentration and the path length, we isolate the observed rotation, alpha. This rearranged equation will tell us exactly what angle the polarimeter dial will show. Continuing our prediction, we substitute our known values into the rearranged formula. We plug in negative 31.5 for the specific rotation, 0.05 for the concentration, and 2.0 for the path length. To simplify the math, we first multiply the concentration and path length together, which gives us 0.1. Finally, multiplying negative 31.5 by 0.1 gives us an observed rotation of negative 3.15 degrees. This tells us that in this specific, less concentrated experiment, the light will only twist by 3.15 degrees to the left, even though the molecule's standard twisting power is much higher. Before we wrap up, let us understand why measuring these angles is so important in the real world, particularly in the pharmaceutical industry. Because diastereomers have different physical shapes, they interact with the human body in completely different ways. One diastereomer of a drug might perfectly cure a disease, while its sibling molecule might be completely inactive or worse, highly toxic. Specific rotation is the primary tool chemists use to check the purity of the drugs they manufacture. By simply measuring how much light a drug sample twists, they can instantly verify if they have the correct, safe molecule or a dangerous mixture. We have covered a lot of ground today. Let us review the key takeaways. First, diastereomers are stereoisomers that are not mirror images of each other, which gives them unique physical properties. Second, we can calculate the maximum number of these 3D variations using the formula 2 to the power of n, keeping in mind that internal symmetry can reduce this number. Finally, specific rotation is a standardized measurement of how much these chiral molecules twist plane polarized light. This powerful tool allows chemists to identify substances and ensure the safety and purity of modern medicines. Great job following along. You now understand the fundamentals of diastereomers and specific rotation.